Welcome to Advanced Patterns for GitHub's GraphQL API. I'm Ria, co-founder and CEO of Toast, and I'm super thrilled to be here in front of all of you and that all of you want to take your GraphQL to the next level. And I really hope that you'll enjoy this talk as much as I did making it. And definitely tweet me if you have any questions. I'll make sure to get back to you. OK, so I wanted to start off with some pre-talk hype. I know it's mid-afternoon, and it's probably tiring. You're probably craving a nap pod. So work with me. I need some energy in the room. Here are some pictures of people who listen to this talk. You'll become a master of GraphQL. You will manipulate code with just your mind. You will put out production fires with a snap of your fingers. And you will be a 10x engineer. But you probably still won't understand monads. But that's OK. It's another talk. All right, let's bring it back. On a somewhat more serious note, we know a lot of people would like better access to the wealth of data that GitHub has. And it is, after all, a hub of all your team activity. So my goal with this talk is to enable you to build your own data fetcher for GitHub using the GraphQL API. And then you can go crazy, retrieve massive amounts of data, and it's all good. And also, we've open sourced our code into a reusable starter kit, so everyone can play. And I believe data should be freely accessible for everyone who is curious to learn. So that's why it's really, really important to me. Disclaimer, though, don't use it for evil. This is not a real license. Don't look it up. I just want us to stay true to the Archimedean oath, which is like the Hippocratic oath, but for engineers. So like other talks today have mentioned, data is pretty amazing and does cool things, like you can use it to identify bottlenecks and unblock your team. This is good. You should be doing this. But data can also be taken out of context and used to make up arbitrary metrics to track engineer performance. This is bad, very bad. And the consequences for misusing the content of this talk and open source library is I will personally be very disappointed in you. So let that sink in. OK, so now that we squared that bit away, I want to provide context about myself and how I got interested in GraphQL. For starters, Toast integrates with GitHub and Slack and notifies engineers when to unblock teammates. And as you probably all know, GitHub has a lot of activity. The bigger your team is, the more activity. So it's very important for us to not simply just pass everything through, and because that would just create distractions for everyone. So Toast filters through this noise and delivers relevant notifications to the person needed for unblocking the team. And we started out as this zero setup notification bot for individual contributors. And since then, we've evolved to empower the entire review process by allowing teammates to respond directly in Slack. And this past year, we've learned so much. And we're continuously growing to meet demands at the team level. And I'm sure you've all been in healthy teams and unhealthy teams. Me too. As such, a huge part of our ongoing work is learning the behaviors and patterns in these teams and alerting them on anomalies before they snowball and get out of control. So to do this, we learn from a variety of orgs with different workflows and habits. And we've needed to build out a robust analytics pipeline for this. So in this talk, I'll share some of the technical challenges that we face along the way. And personally, I have a hard time following super abstract talks. So I thought it'd be nice and fun to learn through building something meaningful. So let's define the problem and the scope. What data should we pull first? Arguably, one of the most interesting aspects of GitHub is code collaboration, where all the learnings and drama happens. So here's a familiar story. We write some code, we send it off for review, it lands in the reviewer's inbox, and after some time they get to it. If we're lucky, they give us some meaningful feedback, plus bonus nits, and we get the review back, and oh boy, we're excited to make all these changes and grow as engineers. And maybe we go through a few more rounds of commits, re-reviews, more changes, and eventually ends up like that, right? But in all seriousness, pull request history tells a fascinating story. And we can learn a lot from the timeline events, the people involved, and how quickly concerns were raised and resolved. So this leads to fascinating insights. Now, I'm not saying that you're going to be able to infer all of this magically, but you can at least start looking through some data. And then you can detect potential triggers that lead to a high-stress working environment, or even get deeper insights like, what is the best time of day to ask for a review? Or learn that large PRs are 3 times less likely to be approved within the first 24 hours. With this, you can encourage best practices and healthy habits for your team. So let's look at our data shape. At the root, there's our organization and some repos. And each repository has pull requests. Y'all know this. Each pull request has lists associated with associated entities, so such as timeline events, reviews, commits, etc., all of those. These are the ones we thought were interesting. So this is a good match for GraphQL, right? It's in the shape of a graph. We're at a talk about GraphQL, so naturally you're all here to learn about this, but I still want to take some time and point out benefits of using GraphQL. So for one, we can pull much more data with fewer round trips. So this entire process is more efficient. Secondly, some data is not easily accessible via the REST API, but we can grab it with the GraphQL API. And as previously mentioned, the GraphQL data model maps conveniently to our mental model of the data shape, so it's easier to reason about. On top of this, GitHub's GraphQL API is one of the better GraphQL APIs out there, and they've really tried, in my opinion, to provide a good developer experience. So that's in itself a good reason to try it out. But if you're not really into any of these benefits, then this talk is probably not very useful for you. But I don't know, maybe you're here for the doodles. I'll be OK with that. OK, so we got our data shape. Let's look at the schema next. So the schema will describe our graph nodes and the relationships to each other. And the good news is GitHub's GraphQL schema is structured exactly like we want. So can we just fetch all the data? It's not that simple. So according to our schema, we want to pull all the pull requests for the org. If we want to do that, we want to first pull all the repos, and then all the associated PRs. So a very simple query would look like this. Notice we specify the organization by name, then the repositories with the argument first 100. And this is our page size upper limit, which specifies fetching only the first 100 repos, which is fine for some orgs. And we also request the first 100 PRs for this repo. And the repos that have more than 100 PRs are out of luck for now. So coming back to our query, there's an obvious problem with this, since we're not fetching all the data. We can get the first 100, but the volume of data that we want may be much larger. How large? Well, it's not uncommon to have thousands of PRs in one repo or more. And for analytics, we need to fetch everything to get that complete picture. How do we tackle this? So you probably all know that APIs and databases solve this by allowing us to paginate. And there are various types of pagination supported by GraphQL, but the most flexible one is cursor-based pagination. So here's a quick refresher. Let's represent the pull requests we want to fetch with these squares and number them for convenience. Now let's line them up. And as I mentioned previously, that the max page size is 100. So for the purposes of illustration, let's just pretend we're going to pull 3 at a time, arbitrarily choose that page size of 3. So these will be the first 3 pull requests that we fetch. Taking a look at our updated query, we just update that number to 3. And also notice that we pull our specific repo by name to simplify our query. So to start paginating, we need to specify not only page size, which is 3, but we also need a cursor. At this point, we don't yet have a cursor, so let's leave that as null. Our return would look like this. But we still want a cursor. To get the cursor as part of our return, we need to update our query to pull an object called pageinfo. That's what it is right there. Now we get a cursor along with pull requests in our results set. Nice. So for context, the results would look like this. Our cursor is just an opaque pointer. It's called endCursor because it points to the last item in the data set we just fetched. So that's what it looks like now. It's pointing at PR number 3 in this case. So for the second page, we just repeat. Simple enough. Page size is still 3, and we provide the cursor that we got from page 1, and we use the after param for this. Pass in the cursor. Here's how our query looks like now. So note the highlight. The $sign in this case denotes the cursor variable that has to be passed into the query separately. Your implementation will depend entirely on your language and library of choice, but this is what it looks like for us. As a result, this query would fetch PRs 4, 5, and 6, and the new cursor, which points to PR 6. Now finally, we can fetch our last 2 PRs by repeating this process. Cool, like this. So we notice that we're using our cursor from step 2 right there. So it's pretty straightforward, this whole path. And now our cursor points to PR8, right? This is our result. How do we know we're at the end? Because we don't want to just keep fetching forever. How do we know we need to stop fetching? So in our return, the list of PRs is contained within nodes, this node's object, and the cursor is actually living in page info, like we know already, with the full name and cursor. Page info also has another property called hasNextPage, which behaves exactly as it sounds. This property is true when there are more pages, and we can keep fetching. It's false when we fetched everything. Straightforward. The updated final query will look like this. Right? Now we can paginate with cursors. Yay! So I know what you're thinking. You're probably like, Ria, hi. This is GitHub Universe, and you're on stage with your little microphone talking about pagination like it's some new cool thing. What am I, a baby developer? Nah, man, I'm here for the advanced stuff. So hold on. Yes, it sounds absurdly simple so far. But what makes it hard? Like, why is this a basis of a talk at all? Well, for one, pagination alone is not enough to pull all the data we need. Pagination is a big part, but there are pitfalls with nested queries, and GraphQL is all about nested queries. We can't just paginate on any query we want. Why? Well, meet this little guy from earlier. You may have noticed him terrorizing my engineers in the opening slides. He's a gotchasaur. This little monster lives in every code base, architecture, complex system, in the nooks and crannies, ready to jump out and delight you with all the gotchas he can find. That's not terrible. He's actually kind of cute to me. But what can surprise you is that these gotchas can turn into much bigger blockers, which can't be resolved without some serious consideration. So let's take a look at the gotchas that are bigger than they seem. So one of the biggest strengths of GraphQL also presents one of the biggest technical challenges. How do we paginate effectively when there are nodes on each nested level that we care about? Do we manage multiple cursors and paginate across every layer? What's an effective strategy for that? A range of other gotchas built on this one. So if you were thinking of just making a massive API call, you'll be hit with the nodes limit pretty quickly that exists on every query. Fortunately, this is something that you can easily calculate yourself before you run your query. Recall this query. Regardless of how many nodes actually exist on each layer, the nodes limit looks at the projected total. So 100 times 100 gives us 10,000 total nodes. What if we decide to fetch comments with our pull requests? My calculation yields 1 million total nodes. That's a lot. GitHub's nodes limit is 500,000, which is already very generous. And if we run our query, we see the following error. Okay? And the good part is GitHub is very explicit about what went wrong. This is a nice descriptive error message, which is very useful. And let's keep this in mind and be careful with fetching nested data, as it's pretty easy to hit the limit. On to our next gotcha. So we know that GraphQL has the power to pull graphs of objects in one round trip. But like everything in life, queries also have a cost associated to them. It's like the price that GitHub has to pay to fulfill your query, and if the price is too high, they'll refuse to pay it. Unlike the nodes limit, cost is not something you can compute for yourself. It's something that GitHub will compute for us, but through trial and error, we can build some intuition around this. So here's how we can check. This is a special type that we can add at the top level called rate limit. Here we ask for two properties, cost and remaining. And remaining is like how much of our query allowance is left. Quick note, this is the primary way that GitHub imposes rate limits on GraphQL requests. Where REST APIs will have a limit of 5,000 requests per hour, GraphQL APIs will have an hourly cost limit of 5,000. And the simplest queries, in my experience, usually cost 1 for comparison. So notice I commented out comments, which we're still pulling 10,000 nodes at max right now. This is still a lot. Guess how much this costs? It's 1. That's a bit unexpected. We're fetching a lot of data, right? So let's add comments back in and go ahead and make a guess in your minds. How does cost change? Yeah, that's a huge cost difference. That's a huge cost difference. With a query this costly, you won't be able to exceed 50 requests per hour, so be wary. And there are many things that can influence cost. The biggest one in my experience is projected amount of nested entities. In this case, it's almost 500K. So use this as an indicator for potential cost, but do experiment. It will vary from different experiences. We will discuss strategies for minimizing costs, but for now, let's just look at the next gotcha. So now that we satisfied nodes limits and cost constraints, the final test is the actual runtime performance of this query. It's not something that even GitHub can predict ahead of time. And sometimes a perfectly fine query that doesn't look like much would consistently time out. And the timeout is fairly aggressive. If our query takes more than 10 seconds, it will fail, unfortunately. So this query only costs 6 points, but 9 times out of 10, it would time out with this error. In our experience, this happens when a query actually returns a lot of data. So here it's attempting to return about 30,000 lines of JSON, which is not that much, only about 12 kilobytes gzipped, but it's a lot for GitHub to compute in a single API call. That's not pre-cached. So note that also cost is just an estimate of how heavy the query is for GitHub servers. And even low-cost queries could time out. This makes designing our strategy complex because we don't know upfront which exact queries would time out ahead of time. So these gotchas are worthy opponents on their own, but in a team fight, they can be overwhelming and present quite the challenge. So let's take a look at the whole request lifecycle in context. We write our GraphQL query that pulls nested data, send it to GitHub servers. They check that our query is below the node's limit. Okay, that passes. Then they compute the cost and add it to our current running costs and check if we're still below our hourly quota. Still in the green, cool. They finally run the query, and if it completes under 10 seconds, then we finally get the result back. Now it's worth noting, nodes limit is something we can compute ourselves, as mentioned. Cost is something GitHub computes, but we can experiment to find out more. And timeouts is, I don't know, just something not we or GitHub can calculate and predict. Sometimes retries help, but most often it means our query is just too heavy and needs to be broken down. And the simplest way to do this is to decrease the max page size and send several lighter requests instead of one heavy request. So I hope this gives you a good understanding of the query lifecycle, and knowing how this process works can help you navigate errors that you will undoubtedly get when you actually start getting your hands dirty. So you can always refer back to this when the time comes. Now that I've convinced you of this sufficiently challenging problem, how do we solve it? So to answer this question, let's recall our data model. Any entities on PRs are 3 levels deep. Let's try to query for comments in this case. So notice we picked 40 as the upper limit for PRs just to satisfy nodes limit. Could have been 100 while we limit comments to 40. It's fine, doesn't really matter much for this example. What does matter is that this query needs to paginate on a nested entity, PRs in this case. And it's very common to have more than 40 PRs in a repo. And if your company has more than 100 repos, that complicates things. But even if we can handle that, some PRs have more than 100 comments. That's even more nesting. So we need a better strategy. The strategy that we came up with is double pass. In cases when we need to pull a lot of data that requires pagination on multiple levels, we can do it in multiple passes. So the core idea behind double pass is that we can first query to collect the IDs of our top-level entity, repos in this case, and then run a query for each top-level entity and paginate on them separately. So this query would fetch IDs and names of the first 100 repos. Now with IDs and names, we can create a new query where we provide one ID at a time and paginate on pull requests. Simple enough. But how do we do this? Typically, GraphQL APIs have a rigid schema. For this to work, we need to find a way to construct a query that fetches repositories by ID or similar alternative. This is from the API schema documentation. So we can either paginate over repos and apply various filters, or we can just pull one repo at a time. The latter seems handy, so let's use that. Now we can run one query for each repository and then paginate on the nested entity, pull requests. We already learned how to do this previously, and this approach works for sure, but it's kind of slow, and it doesn't fully leverage the power of GitHub's GraphQL API. Let's think about how we can optimize this further. If we look closely at a typical organization, we notice that the total number of PRs in repos is very non-uniform in distribution. And it's common to have repos with thousands of PRs and repos with 0 to 10. We can plan our queries better by taking into account the total number of PRs in repos. And if we can get this number without fetching all the PRs, that's great. And it turns out we can, so let's modify our query. This query would fetch 3 repos and a total count of PRs they have. The total count is accessible for every connection in this graph. So for any collection of nodes, we can get their total count without pulling all of the nodes. This is very useful. This is what we return. Now let's see how the PR count fits into our double pass strategy. Okay, so first we run a query to get all repo IDs and how many PRs they contain. To illustrate fetching the result, let's use an adorable puppy. We separate out repos that have fewer than 100 PRs, save it for batch fetching so we don't have to fetch each separately. This reduces the total number of requests. And if the repo has more than 100 PRs, it goes on the right, and we fetch one repo at a time, paginate on pull requests. And then when we're done, we can merge the results on those two strategies and end up with a lot of puppies. So straightforward enough. Let's see it with some data. Here are 7 repos with their counts. I've arranged them in increasing count so we can quickly sort through them into 2 groups. And we're batching these ones into groups where the total is still less than 100. It doesn't really matter how we group these as long as we keep below the max of 100. The bottom line is that now instead of 4 queries, we only need to make 2. For large data sets, this is a lot of savings. On this side, we fetch one by one. It's pretty self-explanatory, using the method we already described for paginating large amounts of nested entities. We merge this together, and we have all of our PRs that we set out to fetch, right? Nice. There's still one piece to flesh out. Let's deep dive into this part. For the repos that don't have a lot of PRs, we would need to construct a query that pulls a subset of repos and their PRs. How do we do this? Specifically, how do we batch? We need to find a way to construct a query that fetches multiple repositories by ID. We've seen this documentation before. It does not allow us to pull data by multiple IDs or by multiple names. What if we just combine multiple repository types into one query? Okay, let's be less confusing with some examples. One approach would be to use GraphQL aliases to fetch several repositories by name. Notice these repo backend and repo web labels. These are aliases, which is just a way to name your data to avoid conflicts in the resulting data set. This would work, but it's a lot more hands-on. We would have to figure out alias names and how to stitch this together. This would either result in a heavier query or require us to use partials, so we're not duplicating our subqueries for each repo. And most importantly, this approach only works because there is a type that allows us to fetch repo by name. What about all the other entities we might need to pull like this? It doesn't seem like a solution that is robust and can be applied generically. Again, fortunately for us, GitHub already thought about use cases like this, and it's one of the only GraphQL APIs that did. But it really should be a best practice because it's pretty great. So what GitHub did is add a special type on the top level called notes type. This allows us to query any item by ID, and it's like a global key value store. So for example, consider this query. Notes is top level that accepts an array of IDs and returns given entities, like type. But because it's a generic type, we can't access any of the repository type properties. We can only get ID and type name fields. So in order to solve this, we need to use inline fragments. It's like a typecast for GraphQL, and we can now rewrite our query accordingly. That's what the syntax looks like. This allows us to access properties on a specific type, and it's a very useful technique, and we can use it to fetch pretty much anything. We can just keep adding IDs to the list, simple and easy. So when we batch, we'll just feed all the IDs from each batch into this parameter and fetch all those entities at once. So you might be thinking, hey, this types thing looks like cheating. Can't I just provide a million IDs and fetch everything in one query? You are right. The normal pagination rules don't apply to this type. It's not bound by the upper limit of 100 items. But in our experience, it's easy to construct queries then that lead to timeouts. And it really depends on how heavy the objects are. In our experience, the reasonable limit would be between 30 and 80 IDs at once. For pull requests with a lot more nested properties fetched, 50 is a good middle ground. These should provide some context for your experimentation. All right, so this all sounds good, but let's make sure we covered and accounted for all the gotchas that we discussed before. These guys. So the nested data problem is solved by double pass by definition, although depending on what you're hoping to do, you might do triple pass, quadruple pass, more passes. Nodes limit, this is simple. Well, we just make sure we don't exceed the nodes limit during query composition. And we discussed optimizing for cost reduction. Let's make sure we handle this. Let's consider this query to fetch reviews and comments for every pull request. If we run it as is, the cost is going to be the following, which is a lot. But we can cheat a little. What do we know about this data? If we think about this query, well, it's very rare when a pull request will have more than 100 reviews or more than 40 comments per review. So intuitively, it just seems abnormal. So I would say it's safe to decrease those page sizes. Let's assume there are no more than 20 reviews, for starters. Run our updated query, and look at that. The cost went down by a factor of 5. Optimizations like this require knowing your data, of course, intuition, and experiments. But it can make a drastic difference, so definitely make sure you play around with this. We at Toast analyzed data from a bunch of companies and picked sensible defaults. So if you're planning to use our library, that's all covered there. Lastly, we have timeouts. This is purely trial and error and running queries in production. What we learned is that the easiest strategy to reduce page size is at the cost of making more requests, or the easiest strategy is to reduce page size. We can reduce page sizes from like 100 to 50 and double the number of requests, but in general, it seems like 50 is a good default to set as a pagination limit for heavy queries. And the last bit I want to mention is a schema preview. The GitHub GraphQL API is constantly evolving, and new features become available often. For example, things like, is my pull request a draft? And are my CI checks passing? These are still in the preview mode. So to access these, you would need to execute your queries while sending HTTP accept headers. It would look something like this. This is a header I use for draft pull requests. And cool, that's it. That was a lot of stuff, a lot of learnings that we just went through. Give yourself a pat on the back if you're still with me, high five. And go build your own GitHub data fetcher. Here's the link to the open source library. It's a work in progress and currently contains starter code. You can use it as a one-off script to pull data for your org and get it as a JSON file. We'll be adding to it more as we build more. So, and feel free to send in some pull requests. And if you're like, Ria, where's the advanced stuff? And this talk is apparently still way too baby level for you. Please, 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 please say hi to me after. I'd love to get your expertise on stuff that we haven't solved yet. And thanks. And you can send me homework reading on Twitter. Yeah, so lastly, this talk was a lot of fun to put together. Thanks for coming, and thanks for listening to me ramble.